Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you everyone for coming out, especially during this week of talks. For the afternoon talk today, we'll have Paul Melstead, who is a student of Alan Fries in the math department at Carnegie Mellon University. And he's going to talk to us today about some models for random graphs. Go ahead.
Thanks for the invitation. It's great to be here. So today we're going to talk about the PageRank and the random surfer model. This is joint work with Prasad Chebolu, also a student of Alan's at CMU. So this model we've been working on is a model for the web graph, and it's slightly more complicated than what we're used to dealing with, but that makes it also more interesting or more realistic, if you will.
When was this proposed?
2006 in Analco. So the model was proposed by Blum et al. And we found an interesting connection to PageRank, and we'll analyze the expected degree and the expected PageRank of a vertex, and we'll find the exact and asymptotic forms for those quantities. And on top of that, we'll see an interesting phase transition in the expected degree of the root vertex, and we'll see what the root vertex is. So before we go into the definition of the model, I wanted to give like an overview of web graphs. You can create your own model if you want. So follow these few easy steps. This is the sort of the generated models. You just put in a new vertex at a time, and you connect to an already existing vertex by your own chosen by your own favorite probability distribution. So it's easier to come up with generated models than to analyze them. And for preferential attachment, which is the sort of mainstream model for the web graph out there, we choose the vertex proportionally to the degree.
So you built a tree here?
Yeah, so we're going to build the tree in our case, and there are, of course, many more variations you can add.
And the random surfer model will also eventually be a tree.
Yeah. And we can add more edges at a time and maybe create a DAG. Or we can also add edges between existing vertices, but this is the basic building block of generated models. And so most of the generated models use local structure. The probability that we pick a vertex as an endpoint is just dependent on the neighborhood of that vertex and not the global structure. For instance, in the preferential attachment, it's just the size of the neighborhood. And we want to analyze models where the probabilities are somehow affected by global structure. It's very loose, but one idea is to take a random walk to choose our endpoint. We start somewhere in the graph, and we take a short random walk, and that's where we put our endpoint. Okay, so it's so potentially we could traverse the whole graph, and that introduces a lot of dependencies. And as Christian pointed out, we're only going to do this for trees because that's the only thing we can currently analyze. So the generated model starts with the root vertex. This is the first vertex of the graph. And we have a self loop there, which is a technical thing. I'll get to it at the end of the talk if we can remove the self loop. But anyway, given the current graph at time t, it looks like a directed tree where everything is directed towards the root. We add in a new vertex. It picks a random starting point. Let's say it picks the bottom vertex out there. And we'll stop there with probability p. We'll keep on going with probability q, which is 1 minus p. Okay? And then say we take a random walk of length 2, and then suddenly we decide to stop, and that's our new graph. We just repeat this over and over again and see what happens. And now...
So you don't do real random surfer in the sense you take a random walk with probability q, and then you do a hop to a random, back to a random vertex, or will that not change anything? It might not change anything.
Yeah, no. So in the next model I'll consider we sort of do that. took an infinite random walk. But see that. So the self loop at the root catches everything. If we are ever walking around in the graph and we hit the root, that's it. We'll just go in circles until we decide to stop. And so once you see the root, you're stuck there. Okay. Yeah. Oh, yeah. It's always a directed tree with a loop on top. Okay. Now, the next model uses PageRank, and so I better explain what PageRank is. For now, we just need to know that it's the stationary distribution of the following random walk. And you can imagine somebody is surfing the web, so each node corresponds to a site, and he'll randomly click one of the outgoing links. So we'll probably see he'll click one of the outgoing links and move to a new website, repeat this, and there's probably one minus C, he gets bored and just randomly restarts somewhere else in the web. I'll do this for an infinite amount of time, and the stationary distribution of this random walk is the PageRank for each vertex. The PageRank algorithm is then basically taking the PageRank values and ordering the nodes according to that. So this deep anthropological insight is the basis for PageRank. Right. And we can compute this by solving an eigenvalue problem.
So in practice, by the way, not every web page has automatically at least one. And what most search engines do in that case, they can formulate it equivalently as they force you to do the restart, or you can say it just creates automatically outlinks to everything.
Right. You have to massage the graph to make sure that you take care of that. Usually you force a restart, and there are lots of variations of how to do that. But yeah. And so that's why I need the self loop at the top, because the root has to have an outgoing enabler. Okay. All right. So the PageRank model is pretty straightforward. We start as before. Just going to show you the directed tree version of it with the self loop. We compute the PageRank of every vertex. We add in a new vertex, pick an endpoint according to PageRank, and that's where we put in our edge. Okay. And it turns out that the models are exactly the same, which is really nice because it's easier to analyze the random surfer model than the computing PageRank every time, provided you set C equal to Q. And the key thing is that it's a lot easier to sample from the PageRank distribution than to compute it. You don't need to know the PageRank distribution to be able to draw a sample from the PageRank distribution. And the idea is, how do we sample from it? Well, we just start somewhere uniformly at random, and we take a short random walk of geometric length, which is exactly the random surfer model. I'll hand wave my, I'll do a hand waving proof to show that they're the same. We just take an infinitely long random walk in the graph and then decide to stop. Think about it, where did we actually come from? Well, we did a restart a couple of jumps ago, and retraced our steps to the last restart. The number of steps we took since the restart is geometrically distributed. And when we did the restart, we started somewhere uniformly at random. So that's it. They have to be the same. More formal proof would probably be easier to do this via linear algebra than probabilities. And of course, this is useful because it's easier to analyze. Okay. And so what we want is the expected degree of a vertex, and eventually we'll also want the expected PageRank of a vertex. And just for comparison, I want to show you how easy this is in the preferential attachment model. It's not a one-line proof, but it's a three-line proof. Let's say a vertex comes in at time tu, then the expected degree is at time t is simply what the degree was at time t minus 1 plus the probability that we picked that vertex. And we can factor it so that it's linear in the degree of the previous time point times this quantity. And then unrolling the sort of conditional expectations, we simply take the product over all time steps since that vertex was introduced. You can write it exactly using the gamma functions, and then this is a known approximation for these gamma functions. So it will give you n over tu, which is your relative age in the graph.
You don't worry about showing concentration or anything? I mean, I know here you're dealing with the expected value.
Yeah, no. In in the preferential attachment model, you can get very weak concentration, say times log n and times 1 over log n. In our model, we haven't yet gotten that. So that is just the expected degree and not concentration. And we don't expect there to be any concentration better than multiplicative logarithmic factor. Okay. So, so the interesting thing is that here the power of the expected degree is 1/2, and we'll see that what it is in the other one. So this is the exact formula for the expected degree of a vertex. It's not very nice, but if for early vertices where they come in at time little o of n, we can write this as n over tu raised to the 4pq. Okay, so there's a completely different dependency on the power there than.
What? No, this is just.
This is for the random. This is the main theorem for the random surfer model. Yes. Thank you.
So P was the
Probability of stopping, and Q was the probability of going on.
1 minus.
Right, 1 minus P.
So wait, it doesn't have a nice representation for times
No.
u of order n.
No. I mean, this will be pretty much a constant. So the theta tilde here hides some logarithmic factors. So this only makes sense for tu equal to little o of n.
But this is an exact formula.
Up there, this is the exact form for the expected degree.
I guess the PIs are little.
They sort of look like log n to the I over I factorial, but not quite. Right. We'll see where they come from later on. Okay. Are there any questions? So how do we keep track of this? The change of the degree of our vertex u will depend on the subtree below the u. Will not depend on anything else than the subtree. So we need to keep track of the subtree, and the subtree, the size of the subtree will depend on the size of the subtree below that, and we need to keep track of everything. Right? You can't just keep track of the, say, first 2 or 3 levels below you. You just need to keep track of every size of everything. All right. So tu is the time when the vertex u is added to the graph, and L sub I of t is the number of vertices at distance I. This is the size of the level in the subtree. And here we take the 0th level to be 1, which corresponds to the vertex u itself. Okay. So in this graph, we have our current
So you say you
figure.
have to keep track of everything. Now, in the ordinary preferential attachment model, you might think you have to keep track of everything, but in fact, you can represent it in terms of pull your earns, and then you don't have to keep track of everything.
Right. Or you.
Because statistically, it's the same as if you didn't and you picked, from a beta distribution. Have you tried to see whether, although this looks like you have to keep track of everything, there isn't a representation in which you get the same answer statistically without keeping track of it? I mean, it's a different process. So
Yeah.
it may not have, but are these exchangeable random variables in some sense, which is what's usually required? No.
I don't think so.
So,
No.
okay.
I think in his time representation, even if the other ones are not exchanged. But
Right, but there was a way of rewriting it so that they are. That's the whole point. The preferential attachment model a priori looks like you have to keep track of a lot, but it turns out that you really don't if you write it in a totally different way. So I'm wondering here, it certainly looks like, I mean, you say you have to keep track of everything, and with the standard way of writing it down in terms of its dynamics, you do have to keep track of everything, but I wonder if there isn't some other representation which you don't. And whether you've looked, I mean, obviously you can't guarantee me that there isn't, but I wondered whether you had looked at that.
No, I didn't look at that. So.
But you know what I'm talking about with the preferential attachment,
Right.
ordinary
Right.
preferential attachment.
Right. Okay. So, so in this case, the levels are, the 0th level is 1, and that will always stay 1, and the other ones can grow. And since the subtree below you is of depth 2, L3, L4, and so on will just be 0. Okay. So let's say we start at the bottom node out there. Moving up twice will cost us a q squared, and stopping there will cost us a p. And so this is basically just the probability that we take a walk of length 2 is pq squared. And so this is how we need to keep track of things. Now, there's only one way to end up at the vertex u, which is to start if you take a length of if you take a walk of length I, there's only one way to end up at u, which is to start at I levels below. Okay. And so Li is the number of vertices at that level, and 1 over t is the probability we pick any one of those vertices. And so we just add this up for all the levels. So this is the probability of increasing the degree by 1. We can do this for every level as well. So we get these formulas for the probability that any level in the subtree increases by 1. And the nice thing is that this is linear in the L vector. So I can rewrite this in a compact form and then look at the expected increase on an L of t plus 1 given the previous value. So it's what we had before times the probability that we wind up at the subtree. So this is actually a vector update equation, something like that. And we can factor it just like we had for the preferential attachment model, like this. So now unrolling the expectation in the same way, we get the expected size of all the levels in the subtree is this product of matrices times the initial vector, which is E0, which corresponds to 1 at the first level and then 0 at every level below that. And what we want is the second coordinate of this vector for the expected degree. And to analyze the page rank, we'll need every coordinate of this vector in expected value. So thinking of this as a polynomial in A, we just expand the polynomial and group together the terms a to the I. And that's where the pi comes from. It's simply it's the coefficient of a to the I. And we have this p to the I as well. So the main problem is analyzing a to the I times e0. And now this is combinatorial stuff. Well, initially we had tried to do this with linear algebra, tried to diagonalize a. And turns out we could find all the eigenvalues, but it wasn't diagonalizable. So we could find the Jordan matrix C composition, eigenvectors, extended eigenvectors. It's about 10 pages of mind-numbing algebra and polynomials and Van der Waals matrices and insane amount of trigonometry. But we could only get the second coordinate, so it really wasn't that good. So we took a step back and fortunately realized that we can just do this by writing this as a recurrence equation. Right? If we know the vector for a to the I times e0, the next one is just multiplying by I, and A has a nice structure. So this is the update equation. And notice we have these q's out there, and when you write out the first few vectors, the q's are pretty easy to determine how they behave. So if you switch to another representation, this little a of I comma I minus k plus 1, you know what the q factor is, and you get this nice recurrence equation for the a's, which are all just integers. Okay, and so the main thing about this is that if we plug in the initial conditions, we see that a0, 0 is 1, ai minus I is 0.
So this is not, the solution is not some well-known special function or something? I mean, if you sat there with these big fat books of recurrence relations leading to certain special functions.
Yeah. Well, once we rewrite it, we'll see what it is.
Oh, okay.
And it's one of those well-known things.
Okay.
Yeah. But you have to rewrite it to see it.
Okay.
Okay. So, right. So what we know is that a0, 0 is 1. ai minus comma I is 0, and notice that it's above the diagonal. So all the things that are on the diagonal or below are going to be they're going to be positive integers. And the update equation for the general term ai, a minus k plus 1 is based on, well, all these points out there. Okay? And so what we can say is that this is equal to the number of paths, lattice paths, which move either to the right or up, that start at 0, 0, wind up at the point out there, but never cross the diagonal. Okay? They can be on the diagonal, but they can never cross the diagonal. So that's what this I minus 1, I equal to 0 says. You can never actually cross the diagonal. And this is just, this is a well-known formula. This is the, these are the ballot numbers, which correspond to, if 2 candidates in a race, one of them gets I votes, one of them gets J votes. What's the probability if there's a random counting of the votes that one of them will always stay ahead of the other? And which is relevant these days. But plugging in, we get this expression, and well, that gives us this formula here. So this has nice connections to to the Catalan numbers. For k equal to 1, this is just the Catalan number. And for k greater than 1, this is the kth convolution of the Catalan numbers. Nice to see some combinatorics here. All right, so plugging in for k equal to 1, we get this expression, and well, now we see where it comes from. We have the p sub I, which was this nasty collection of t terms. We have pq raised to the I, and then times the Catalan number. And now we can use the approximation for the Catalan number. It's roughly 4 to the I, over I to the 3/2. And then all the contribution of the sum comes from I.
Might look nice than half line, but anyway, don't. I'm just saying that when you get into these numbers, you actually often do want to take them into the complex plane. So I'm like, oh no, that's a different one.
No, I is always an integer here.
An integer.
Yeah. Okay. So all the contribution of the sum comes from when I is roughly log n. So we can just take the I to the 3/2 outside and approximate this, where we don't care about logs anymore. In this way, right? We have a 4 to the I, pq to the I. And this can be converted exactly into this form. And from what we did before for the preferential attachment, we know that this is n over t raised to the 4pq. So this is where the 4pq comes from. Okay. So that was the expected degree that has this sort of power law. Well, not a power law, but early vertices have high expected degree, a lot higher than you'd think. And now we can also use this to analyze the expected PageRank. The PageRank, we just think about the PageRank as a numerical value, and of course the PageRank is a random variable in what graph we actually wind up with. And we look at the expected value of that, and that's equal to the expected value of the probability that we pick u times n plus 1. And it's linear in the levels. The PageRank is linear in the levels, so the expected PageRank will be linear in the expectations. And we know the expectations are everything. It doesn't look nice, but now we have a double sum, so we don't think about this twice. We reverse the order, and and now the expression out there, k going from 1 to I, will actually simplify to the ith Catalan number. And, more combinatorics. And then this is just the expression we had for. This is just the expression we had for the degree. So this is n over tu raised to the 4pq. There's a 1 over n missing out there. So this is actually n times the PageRank, since the PageRank has to sum up to 1. Okay. So the PageRank follows the same, or the expected value of the PageRank follows the same power law, if you will, that the degree does. Okay. But now we get to the root vertex. Because it had a self loop, every walk must stop there. And remember when we derived the update equation, we had this p in front, which corresponds to the probability that you stop there. But if you ever hit the root, you will stop there. So the only difference is that there's a p missing out there. And instead of p times a, we had this a tilde, which is just the same, except the first row is missing as a p missing out there. And this is harder to work with. But the nice thing is that as p decreases, we're less likely to stop, which means we'll take longer walks. So we're more likely to connect to the root. Okay? And the degree of the root will be stochastically decreasing in p. And if you look at the fact that a tilde is greater than p times a, we can use the previous result for p equal to a half and say a regular vertex would have expected degree that's theta tilde and n. So the root will have more than that. And of course, the root can have more than n minus 1 in degree because that's all the vertices in the graph. So I can say that the expected degree of the root is somewhere between n and n divided by some logarithmic factors. And so this holds for every p from 0 to a half. The expected degree of the root doesn't change a lot. Now this is even uglier than for a to the I. This a to the I, a tilde to the I times e0 sub k. We can derive the formula. It's not nice. And show, using some approximations for upper bounding, that for p greater than a half, this turns out to be n to the 4p cubed. I'll go through that. So the expected degree is n of the root is n raised to the gamma, where gamma is either 1 or 4p cubed, depending on whether p is less than or greater than half. So the expected power, or the power of the expected degree looks like something like this, which is
This is the
weird
expected
behavior.
degree of the root,
Yeah.
as opposed to the expected degree of the rest.
right. For the rest of the vertices, you'll see the other part of the quadratic 4pq coming up
So
there.
for p bigger than a half, it's looking like the rest of the vertices.
Right. There's the root isn't that special, and for p less than half, it's really special. It's a really special vertex. Okay. So that's sort of weird. It's not something you expect to find in the web graph, which means that sort of this is a toy model, unless we can remove the self root. Okay. So now some open questions. We only get the expected degree of a vertex, and it's only really useful for vertices that come really early in the process. I have some ideas of how to do this for low-degree vertices, but the recurrence equation is just horrible, so I can't solve it. The self-loop at the root vertex is artificial. I mean, because we have the self-loop, we get this phase transition in the degree of the root. And we'd like to get rid of that. But if we do, the update equation is no longer linear in the L vector. So can analyze that as well. And then if we extend this to DAGs, adding more than one edge at a time, we no longer have the property that there's only one way to wind up at a root. Things get even worse than before. Okay. That's it. Thank you. Let's do that. Questions?
Well, I guess I guess in hindsight, this is more of a comment. Maybe there's a question in here.
Mm-hmm.
I guess in hindsight, with the ordinary preferential attachment model, or when you compute PageRank, the biggest contribution, or like the lowest order of contribution, is just how many of your neighbors point to, is just the integrand. So here what's going on is that instead of surfing by degree somehow as you do to calculate PageRank, you're surfing by PageRank.
Yeah.
And I guess it wouldn't be that surprising that in the end the degree distribution
Would-
turns out to have the same power as PageRank,
Yeah,
right?
yeah.
I mean, in hindsight.
Yes, hindsight.
Makes a lot of sense in hindsight that they
Right.
have the
And-
same degree distribution.
Right, and this is, we know, for instance, that you can construct models or construct graphs where the page rank is wildly different from the degree.
Right.
And it turns out in preferential attachment, the page rank distribution is pretty much the degree distribution as well.
Right, right, and that's
So,
what I'm saying. And,
yeah.
and to lowest order it is, and
Is that
then
proven
and
in
then there are
PageRank? Is that
deviations
for
from
the
it in
standard
here.
ones that proven?
Yeah, yeah, yeah.
Deviations are
Is
gone.
that proven for the standard preferential attachment?
For slight variation of the standard preferential attachment.
So what is that?
I can't remember their names. It's in internet mathematics, the most recent one.
What if you didn't do an oriented tree, so that your random walk would walk on?
Then the page rank is simply the degree. So for an undirected graph, the page rank is just the degree divided by the number of edges. And then you have preferential attachment.
Is that honest? So why is that?
If you have undirected, if you think about edges going in both directions, the random
Stationary
walk is
random walk is degree, but the restarts don't bother you?
no. It's the Markov chain for the infinite random walk is time reversible, so it will just be the degree distribution or the preferential attachment.
Okay,
Yes,
something on
Question?
What type of results? So you mentioned that the page rank and the degree are the same for some models.
Mhm.
So like, what type of how do they approximate each other, like the degree and the page rank? Is it additive or what's the? Do you remember any?
The only thing we show here is that they're of the same order for. They have roughly the same for this NOT raised to some power. This is both. This was shown for the preferential attachment one and this one here. But I haven't seen PageRank analyzed for any other models. So, or at least any other random graph models.
All right. So Paul's going to be here at the Friday. If people have more questions and you want to catch them afterwards. Thanks again.
Thank you very much.